Hey guys, Mrs. Saller here. Just wanted to give you guys just a couple more examples to look at before you start your homework tonight, in case you need it, because I know this cross-sectional areas or cross-sectional volume stuff can be a little tricky, especially to visualize and things like that. So I just want to go through a couple more examples from today's notes, and I'll do one homework problem that you guys have to do for tonight. So we're still doing volumes using cross-sections to find those volumes. But I'm going to look at two different examples that are a little bit different than the ones that you're going to see in the book and also the ones we did in class. So let's say, for example, that we want to find the volume of the solid that is created actually creating it by going between the graph y equals root x and the x-axis is our base region. And then also the cross sections are equilateral triangles, perpendicular to the x-axis, between the values 0 and 9 for x. Okay, so the first thing you want to do, as usual, is you want to look at a graph of this. So let's take a look at a quick sketch. So we have the graph y equals root x, which is our typical y equals root x graph. And we're just going to go between 0 and 9, so we're going to stop once we hit 9 over here. And this is our base region, so this is where we're going to stack those equilateral triangles vertically, so they're pointing out at you on the screen. So we're going to put little equilateral triangles that are perpendicular to the x-axis, and they're going to be sticking out at you. So you're going to have like a pointy shape pointing out at you. So I guess this is kind of really hard to draw, guys, but kind of picture these triangles jutting out of the page at you. Okay, they're putting them vertically on the page. And you're going to have an infinite number of these. Okay, there's going to be tons of these. I'm just giving you a sampling of them. But as you move to the right, they're going to keep getting bigger and bigger and bigger and bigger. So you're going to have like this weird bean shape when you're done with this thing, and it's going to be pointing out at you. So your first task, and really the hardest task of these, is finding the area of one of these triangles. So one of these sides is a y value. And we know what y is equal to. It's equal to x, or root x rather. So this side will be root x, this side will be root x, and this side will be root x. So when you're setting up your area formula, the area of all these triangles, regardless what x is going to be root 3 over 4 times side squared. So root x squared. So what does that turn out to be? Well, it just turns out to be root 3 over 4x. So now we need to find all of these areas and add them together, okay? And that's going to give us the volume. So if I think of all the possible triangles you could stack here and add them together, that'll give me the volume. So the best way to do that is take an integral. So we're going to take the integral from 0 to 9 of our cross-sectional area, so of the root 3 over 4x, which I'm going to factor out the root 3 over 4 because it's just a constant, and we have x dx. So now it's just going to be the calculus that comes in. So usually this is where people have most trouble. If you can set this area up, you're golden, because this is really not a bad integral. So when I take the integral of x, I get 1/2 x squared, and we're going to integrate that from 9 to 0. Okay, so this is really going to be root 3 over 8 x squared, and we're going to evaluate that from 9 to 0. So when you plug 9 in, you get root 3 over 8 times 9 squared, minus when you plug 0 in, you're going to get 0. So as a result, the area we get is 81 root 3 over 8, and there's really not much else I can do with that, so I'll just leave it as it is. So this will be the volume of that goofy shape that's created when I stack all those little triangles together. So once you find that cross-sectional area with respect to x, because obviously all these triangles' areas will be different depending on what x is, you just take the integral from whatever to whatever, in this case 0 to 9, of our cross-sectional area with respect to x. So let's do one from the homework tonight that you guys had to do, which let's take a look at number 4. Which in number 4, it says the solid lies between planes perpendicular to the x-axis at x equals -1 and 1. The cross-sections perpendicular to the x-axis are circular discs whose diameters run from the parabola y equals x squared to the parabola 2 minus x squared. So they give us this great picture here, and I will not even try to do as good a job as them, but they do a pretty good job giving you a good picture here. But our two graphs are x squared, so just our typical x squared graph. So that's y equals x squared. And the other graph is 2 minus x squared, so up 2, upside down graph. So that's our graph y equals 2 minus x squared. And the cross sections are going in between these two, and they're circles with diameters extending between them. Okay, so this, you'll have a circle kind of jutting out top and bottom at you. Okay, so it's going to be jutting out at you and jutting out to the bottom. So you have like a football shape. If you kind of picture what this is going to look like, it's going to kind of look like a football as you go right and left forever on this thing. Okay, so we need to figure out what this length here is. So when we think about what that circle looks like, we're looking for that length right there, okay, that whole diameter. So that whole diameter will just be top function minus bottom function. So this whole diameter will be 2 minus x squared minus x squared. So it'll be equal to 2 minus 2x squared. But we need the radius. If we're going to find the area of these circles, we need to take that and divide it by 2. So when I divide it by 2, I get 2 minus 2x squared over 2, which is equal to just 1 minus x squared. Okay, you divide both those by 2, you get 1 minus x squared. So the radius is 1 minus x squared. So to get the cross-sectional area, a of x, we're going to take pi r squared. This is just a circle. So pi times 1 minus x squared squared. And we're going to take that and do the integral. Now, I don't know about you guys. I'd like to avoid using u substitution, which you'd have to do here if you didn't multiply it out. And I'm going to multiply it out, just so you can just do reverse power rule, and it'll make it a lot easier. So this will turn to pi times, we have 1 minus 2x squared, you multiply that out, plus x to the fourth, just do a little foiling there, guys, and there's our cross-sectional area. So to get our volume, we're going to take the integral between, well, we're going between negative 1 and 1. They told us where these intersected. So between negative 1 and 1 of pi, I'm going to factor that out, 1 minus 2x squared plus x to the fourth, with respect to x, and we're ready to take the integral. So again, guys, this is not a terrible integral. This was kind of a pain to set up, but once we got it set up, the integral is going to be actually pretty nice. So now let's take the integral. We're going to have pi times the antiderivative of 1 is x, minus this guy will be 2/3 x cubed, plus this guy will be 1/5 x to the fifth, and we're going to evaluate that from negative 1 to 1. So let's plug 1 in. We get 1 minus 2/3 plus 1/5, minus when I plug negative 1 in, I get negative 1 plus 2/3 because the double negative, and then minus 1/5. So now let's add like terms together. So we have 1 plus 1, which is 2, and then negative 2/3 minus 2/3 is minus 4/3, and then 1/5 plus 1/5 is plus 2/5. And now we just need a common denominator. So let's multiply to get 15. So times 15 over 15, times 5 over 5, times 3 over 3 to get that common denominator we need there. So we have 30 over 15 minus 20 over 15 plus 6 over 15. And when you add those up, you get pi times 10 plus, so 16 over 15, which means our final answer for the volume is 16 pi over 15, and we've now just found the volume of that goofy football shape. So hopefully this gets you guys on track. We're actually going to do more examples like this one tomorrow, but we just didn't have time today to get to one where we have to subtract the two. So hopefully this gets you through number 4 tonight. And otherwise 3, 5, and 6 should look a lot like the ones we did in class. So look at your notes, look at that opener we did in class, and hopefully that gives you guys all the tools you need to kind of tackle this cross-sectional volume stuff that you guys had to do for tonight. Thanks so much, and I'll see you guys tomorrow.